Every semester since I started teaching, I've been chasing after this sort of unicorn of being able to completely prepare my course before it starts. So every August, for example, I think to myself, okay, this year I'm going to get my whole fall course prepared in August, so all I have to do in September is walk in and give the lectures. And every April, I think, okay, this year I'm going to get my whole summer course prepared in April, so all I have to do is walk in and give the lectures. And the same is true in 2021. So in 2021, for this particular course, I had to come up with everything from scratch, all these slides and everything brand new. And for once, for whatever reason, maybe the pandemic, I actually started doing that in advance. And by mid-April or so, I actually had most of the course ready, in fact. And I was thinking, finally, I've done it. I've reached this milestone of actually being able to follow through on preparing the course in advance. And then I hit this topic, and everything just ground to a halt. I thought to myself, okay, this topic is called the network simplex method. We'll see in a few minutes that it involves something relating to graph algorithms. And I thought, well, this is great. My background is in graph algorithms. This topic is close to home. It should be easy to come down the home stretch and finish preparing the course. But that didn't happen. I started on these slides in late April, and they just wouldn't go. For whatever reason, I would come back every day and say, well, I've got to make up more slides for this topic. And just nothing happened. After a while, I figured, I guess I must have writer's block or something. So this is a topic that's covered, I think, very well by Vanderbee's book. But like other parts of Vanderbee's book, the derivation that's given explains how to use the method and justifies algebraically why the method works. But it doesn't spend very much time explaining sort of the intuition behind this method. Not just algebraically why it works, but intuitively in terms of graphs, because it's a graph application. Why does it work in terms of the graph? How do we interpret the graph? And I spend a lot of time staring at it, thinking, okay, I can do this. I can use this variant of the simplex method, but why does it work? What is the significance? And so day after day I came back and I sort of stared at these slides. I idly stared at these incomplete slides for the last 2 months. And as a result, unfortunately, here we are in the first week of July, and I've only just gotten them finished just in time. So I want to tell you a story about writer's block. So I started in late April on these, and then I froze up. And then the course started in May, and of course there's a bit more work to do once the course starts, giving assignments, marking assignments and things. And I kept coming back to these and wondering, what am I supposed to do? What do I need to get these finished? And after a while, I actually began thinking, okay, is there something that I'm missing here? Do we need to are there strategies to tackle writer's block? Is there something I can use to inspire myself? So I went out and started watching old movies. I rewatched the movie Network from 1976. I watched the movie Primal Fear from, I think, 1996. And I watched the movie The Dualists from, I think that was 1977. And I mean, while we're on the subject, so this is Primal Fear. Sounds really exciting. Not really a horror movie. It's a movie about lawyers, and it's not really even that good of a movie. Like, not really much substance to it. I mean, no style either, because it's the mid-90s and it's got all this 90s fashion, and it's like these people are basically just wearing a tarp. Then there's this movie, The Duelist. This is about people that fight duels in 18th and 19th century France. And I usually like historical dramas, but not this one. On the other hand, this is a great movie. I've got a nice quote from it here. Despite what it sounds like, it has absolutely nothing to do with linear programming or this course or computer science or anything else, but it's a good movie. I think UVic actually, through the library, has access. They've given every student access to a streaming service with all these movies on it, so maybe I'll put a link on Brightspace. Not that you need it for the course or anything. And I watched these movies, I stared at my incomplete slides, and I tried to busy myself with other things that made me feel like I was getting something done, like I installed better soundproofing in my office at home. But then eventually what happened was, I think as often happens with cases of writer's block, I got close to a deadline, so the beginning of July began to approach, and I realized sooner or later I'm going to have to actually give this lecture. And I thought to myself, all I need is this one lecture on the network simplex method. Come on, you've done, harder things than this in your life. Just sit down and start making these slides. And eventually, just like a student who procrastinates on an assignment until the day it's due, for whatever reason, the motivation just suddenly showed up. And the slides started coming. And they didn't stop. And I think by the time the dust settled, we have enough material in this one topic to take us right through to the end of the course. And so networks, and in particular, the network simplex method, will be our very last topic this semester. And so we'll begin on this 2-week odyssey by talking about that word, network. So we know already that linear programming was invented, or the simplex method was invented, and the modern notion of linear programming coalesced around the 40s and 50s, or the 1940s and 1950s. And it turns out that at the time, graph theory terminology wasn't very well established. Because graph theory itself is actually a relatively new sub-area of mathematics. And so this style of problem was called a network problem. And you might have heard about network problems before in a different course, and I'll address that a little bit in a minute. But certainly when I look at this, I, coming from a graph theory and graph algorithms background, I look at this thing and I say, that's a graph. I don't see the point in calling this thing a network. To me, it looks like, well, there's some vertices and there's some edges. Sure, edges have labels attached to them, and vertices seem to have some sort of label attached to it. In my mind, that's just a graph. I would treat that not much differently than any other graph. Calling it a network seems unnecessary to me. But in any case, we're stuck with this terminology, and this sequence of lectures is going to cover a very particular set of these graph theoretic problems. It's a broad set, but it is pretty well defined, that can be solved by a variant, a specialization of the simplex method. Now, these are called network problems for a lot of different reasons, one of which I think is because the name was attached to these problems before much thought had been given to the modern graph terminology. Although I would argue, as I did a minute ago, that a lot of them aren't that much different, and a lot of the things you have to do with them aren't that much different than the fundamental graph algorithms that you might have used in a previous course, like CSC 225. We're going to notice, when we get to parts 2 and 3 of this sequence, that we're doing things like finding paths between vertices using traversal algorithms, and we're looking for spanning trees, and we're looking for cycles in graphs. Now, on the other hand, we've also got this problem, which is here we are in the prologue of this topic, and we're already going to be stuck in notational hell, which is that the sources that I've seen that cover this from a linear programming angle, so Vanderbee's book, but not just Vanderbee's book, other linear programming textbooks, tend to want to use some terminology that seems to be unique to coverage of this as a linear programming problem. So in other words, it isn't really consistent with all of the graph theory terminology you probably saw in CSC 225. That bothers me. That bothers me for a couple of reasons. One of which is we've all gone and learned this terminology. We should use it. We shouldn't have to come up with a brand new set of terminology for this one application. And the other one is I don't like the idea of, in some cases, redefining existing terms to have some new meaning for this one application. So what I'm going to do, and you're used to this by now, that my sort of weird grumpy way of complaining about people modifying notation, I am going to choose to use pretty much standardized graph theory terminology. I'm not going to try and use the specialized linear programming form of the terminology. I don't think it makes anything less clear. I hope it actually makes things more clear because hopefully you already know all this terminology. Then there's this other problem, which is that we're going to notice that for basically all of this lecture and the next one and the one after that, and I think all the one after that too, we're going to be talking primarily about one particular type of network problem, which is formally called the minimum cost network flow problem. You have likely seen some variant of a network flow problem before, for example in CSC 226 or perhaps in CSC 425, 520. Which was likely the max flow problem, which is where you have a set of vertices and you have edges between them, and you are allowed to send a certain amount of flow across a particular edge up to some limit. So I could send 4 units out of the 5 that I'm allowed to, or I could send 5 units or 0 units, but I can't send 100. I can't send 6. If the idea of flow and edges is alien to you, don't worry about it. I will define that in a couple of minutes. So that style of problem, where each edge of the graph has a capacity, and you can send some amount of the resource across the edge up to that capacity, that is what we would call a max flow problem. It is not the problem we are going to cover today. We're going to cover a different kind of network flow problem that actually turns out to be sort of one of the most fundamental ones. We'll see eventually that we can convert a max flow problem to one of these minimum cost flow problems. The issue is that Vanderbee just calls this a network flow problem. the problem that we're going to cover. I may do that myself a little bit, but to be clear, there are lots of different variants of network flow problems, and we should be careful not to mix them together because they all can be solved by slightly different algorithms. One thing that's worth observing, if you are familiar with those max flow problems, the kind that in CSC 226 you might have solved with the Ford-Fulkerson or the Edmonds-Karp algorithms, or in particular, if you recall the max flow min-cut theorem, which is one of my favorite things out of CSC 226, it turns out all of that max flow problems can be solved with this network simplex method, and in particular, this really important theorem is in fact a special case of the duality theorems of linear programming. We can prove it pretty easily by just using duality. So it's one example of a case where duality provides us a lot of theoretical tools, not just something that we can use to solve LPs. All right, that all said, so all disclaimers aside, fine, what is our application? What is this minimum cost network flow problem? I'm going to build up to it because there's a lot of different pieces, and depending on your background, I expect everybody who's in this course understands basic graph algorithms, so you know what a graph is. You understand the basics of representing a graph inside of a computer, and implementing the most basic graph traversal algorithms, which are called depth-first search and breadth-first search, and I abbreviate those DFS and BFS. We don't actually need to use DFS or BFS for the most part for the sake of these lectures, but I'm assuming everybody has at least that amount of background. Additionally, if I talk about things like paths or cycles, I assume that people have heard those terms before as well. Of course, if it's been a while and you're rusty on that, I actually think that I love graph theory, and so maybe I'm biased, but I think those are terms that are pretty easy to refresh your memory on. They're pretty intuitive. So first, what is this network that I keep talking about? Well, the network is going to be a directed graph. And in my mind, I would rather just have talked about this whole thing in terms of directed graphs. Calling it a network seems unnecessarily mysterious. But in any case, these networks will be directed graphs. So what is a directed graph? A directed graph is a combination of a bunch of vertices, which will be stored in a set called V. And vertices are just some set of mathematical objects. You might know if you represent a graph in a computer, you might use integers to stand in for your vertices. And then we have a set of edges. And edges are ways of making pairwise connections between vertices. Inside of a directed graph, an edge is an ordered pair. So this edge would be the ordered pair di. The key thing is, in an undirected graph, we don't care about the order of an edge. We would just say, di, so the edge between vertex I and vertex D. We can call it di, we can call it id, who cares? But in a directed graph, we do care because we care about this direction. We care that it points from D to I. And so we use this ordered pair representation where the first thing in the ordered pair is the source and the second thing is the destination of the edge. So the edge always points towards this second element of the pair. I belong to the school of thought that says that as long as we all agree that we're talking about a directed graph, it's fine to just call these things edges. There's no need to call them anything special. In the event where we need to disambiguate, I actually tend to like calling them directed edges because I don't like introducing extra words for things if I don't have to. On the other hand, the term arc is widely used to refer to directed edges. Even I do let that one slip sometimes. Even I use the term arc every now and then. If you hear the term edge or arc in the context of this course, we're talking about directed edges. For this application, now I know there's that word that we don't like, but we'll see that this resolves pretty easily on the next slide. For this application, I'm going to assume that if you provide me an input, and the input will be a directed graph, that the input that you provide is what we're going to call weakly connected. And there's one weird issue with this application, which is there are some times when the directedness of the graph isn't significant. We talk about things like connectedness and spanning trees, and really deep down we're only talking about the underlying undirected graph. We're ignoring edge directions. So I'm going to make the assumption that if you hand me an input, that it is weakly connected. So a directed graph is weakly connected if, when I just delete all of the edge directions, which gives me back an undirected graph, that undirected graph is connected. And recall that an undirected graph is considered to be connected if, when I choose any two vertices, there exists some path between those two vertices. I will deliberately choose a very circuitous path here. Okay, so if I were to choose any two vertices in this graph, I would be able to find some path between them. Therefore, this undirected graph is connected. And if this is the undirected graph corresponding to some directed graph, that directed graph is now weakly connected. So you might recall from CSC 225 that there's also this specialized definition of connectivity for directed graphs called strong connectivity. A directed graph is strongly connected if, when I choose any two vertices, let's choose E and C. If I choose any two vertices in my directed graph, I can find a path from one to the other and a path that goes back. And so in this case, there is a path from E to C and there is a path from C to E. On the other hand, in this graph, if I were to choose D and C, well, there is a path from D to C. But you might notice there's no way that there's going to be a path from C back to D because there are no edges pointing inwards to D. So this graph is not strongly connected, but we don't care. It turns out for our application, all we care about is weak connectivity. Now, then there's this question about why I'm allowed to assume that. So if you hand me one of these input networks, what our goal is going to ultimately be is to move stuff across these edges between vertices. And if you were to hand me a network that was not weakly connected, so here's an example of a network that is not weakly connected, because I can, if this is one big graph, notice that there is no way to transport things between this side and this side. So it's not weakly connected because, for example, there's no path from I to H. If you hand me a graph that's not weakly connected, what I could do is always just split it up into two pieces, two smaller weakly connected graphs, and just solve the problem separately on those. That's why I'm saying we're going to assume that my input is weakly connected. I'm not really making this claim that all of my inputs are weakly connected. I'm saying in the event that you give me one that isn't, I'm just going to decompose it into two or three or four or whatever weakly connected pieces and then solve the problem separately on those. Because there are no edges between the different pieces, there's no way that the solution that I have over here could really interfere with whatever solution exists over here, if one exists. Now, one more definition that's a bit weird, that's sort of halfway between directed and undirected, is this one. And I was really uncomfortable with using this term. Back in April, when I started thinking about these slides, I really didn't like that this term was used. Obviously now, given that I ran out of time to complain about this, I'm okay with using the term. I think that there are no alternatives. The issue is that I like the idea of a spanning tree being something defined for undirected graphs only. And it turns out that the definition of spanning tree used here actually is the undirected one. The directions of edges are being ignored when constructing these things. But I need to explain this a little bit further because it is still a very unconventional use of that term. So typically a spanning tree of an undirected graph, so here's an undirected graph, a spanning tree of an undirected graph is some connected acyclic subgraph of this undirected graph. So I could produce something like this. And you might recall that normally, if you were to run any traversal algorithm on the graph, on a connected graph, the set of edges that are explored by that traversal algorithm will correspond to a spanning tree. Okay, so here is, I think this is good. Yeah, here's a spanning tree. Notice that using the edges that I selected, it is possible to get from any vertex to any other vertex. So it is a spanning tree because it is a connected and acyclic, there are no cycles, subgraph of my original connected graph. The issue here is that we have a directed graph, and we're still talking about spanning trees. And typically the definitions we use for trees don't generalize to directed graphs. You'd use some other terminology to describe the equivalent of a directed tree, maybe an arborescence or something. And so I'm a bit uncomfortable with this. On the other hand, what's really happening in this application, what we're going to see, we'll see this in the next lecture, is that when I talk about spanning trees of my network, what I'm really talking about is a spanning tree of the underlying undirected graph. And hopefully you'll notice if you delete all of the edge directions here, and you consider this thing as an undirected graph, what I've highlighted is indeed a spanning tree of that. So that's one very particular piece of terminology that I want to add a nice big fat disclaimer of right here, that I get that the word spanning tree really shouldn't be applied to directed graphs, but I think there's no better word for it in this context. It is a spanning tree of the undirected graph that underlies the directed one, and we're going to need to talk about spanning trees so much in the next few lectures that this is actually a pretty convenient term. There really isn't any more convenient term for it. And the slides are now giving the same disclaimer I just gave. Okay, so then the question is, what is our application? So it's formally the minimum cost network flow problem. And usually these are contextualized in terms of the graph representing, for example, a set of cities on a map, and the edges between vertices representing some kind of transportation mechanism. So for example, we often talk about this because we call it a flow problem. We might say that all of these vertices are cities and the edges represent a pipeline network between them. And for a lot of different reasons, I'm going to say that the pipelines, for the sake of this course, are carrying water. So suppose that I have water pipelines that can go from city I to city E. And for whatever reason, they are one way. I can only send water from I to E or from E to G. We can also think of them like power lines or something, so I can send power from I to E and from E to G and from G to F. And there might arise a situation in which whatever resource I'm talking about, water or power or maybe, unfortunately, some fossil fuel or something, whatever resource I'm talking about might have a greater supply in one city than another. There could, in fact, be oversupply in one place and demand in another. And the question might then be, how do I equalize supply and demand? So for example, suppose at city D, I've got 5 extra units of my resource, of my power or my water or whatever other set of goods that I'm shipping. So I've got a warehouse full of something that I want to ship to my other cities. I have 5 extra units of it here. Whereas over at city G, there is a demand for 5 units of power or 5 units of water. What I could observe is that if I send 5 units across these edges, then this oversupply here will get balanced by this demand here. And fundamentally, that is the underlying application. I've got a set of cities on the map, and I'm talking about some resource that is oversupplied in some places, and it's in demand or in a shortage in other places. And my goal is to balance that out. And I also want to balance that against the cost of shipping these goods. So, because we don't want to talk about the application in terms of water or power or whatever, or sofas or anything, we typically call the resource that we're shipping between cities, we just call it flow. So I would say something like, I want to push 5 units of flow from city D to city I. What that means is I want to send flow along that arc. Now, because arcs have directions, our ultimate goal is going to be to ensure that directions are always respected. So that is to say, I'm allowed to send 5 units from D to I. I'm not allowed to send, in the grand scheme of things, once I'm done with all of this, I am not allowed to send 5 units backwards, because there is no edge that points backwards from I to D. There's only an edge that points from D to I, and I'm required to respect edge directions. However, in the meantime, we are going to define a convention for what if, in an emergency, we do decide to send flow in the wrong direction. So I could send 5 units from D to I. We're going to adopt the convention that if for some reason I really, really want to send flow backwards along an edge, so in the wrong direction, I will just view that as sending a negative amount of flow in the right direction. So if I say I want to send negative 5 units from D to I, what I'm really saying is send 5 units backwards from I to D. And I know that's a bit odd that I would define that even right off the bat. It turns out that, of course, in the grand scheme of things, we don't want that. But having a way of representing that in an intermediate sense, that we have some flows that are invalid, that they go backwards, does actually help us out. It allows us to iteratively improve a solution. Okay, so what do we need to model this problem? We already have our cities on the map, and we have the connections between them. We need some way of modeling, well, first, how much of the resource is available at each city, and how do I send it between cities, but also maybe some notion of if I have multiple different ways of conveying the resource between places, what's the best one? So an example would be, let's see, if I'm sitting at city E, and I need to send, so suppose that there is a demand of 10 units of flow at city H, and E has an oversupply of 10. Well, then I guess I could just send 10 units down from E to H. But maybe city E and city H are separated, I don't know, by a bunch of mountains or something. And if I were to send stuff directly from E to H, that might cost a lot of money. Maybe it's actually cheaper to send it all the way down like this. I send it all the way around from E to H the long way, or I don't know if it's actually the long way. I send it around with a bunch of stops. We know that because of the way we use graphs to model stuff, we actually have no idea which way is physically longer or whatever. We just know that there is a way of transporting flow from E to H either directly or with a bunch of intermediate stops. And we don't necessarily know which one's better. We need some way of modeling that so that we can choose the best route. And we'll model that by basically assigning a cost to each arc. We'll assume that we want the cheapest possible route, and we can decide to model cost based on whatever factors we want. All right, first, we need to model how much of our resource is available or in demand at each vertex. And we will choose to do this by modeling the total oversupply at each vertex. So we'll call these supply values. But to be clear, what that's meant to imply is that if I say that vertex D has a supply of 10, that means vertex D has 10 extra units of my resource. I mean, internally in vertex D, like maybe there's a power plant at vertex D. So if I have 10 extra units of power, maybe vertex D, city D, uses 20,000 units of power, but it has 10 extra, 10 that it doesn't need, an oversupply of 10 units. Meanwhile, vertex I has a shortage of 5, and we'll model that by a negative supply. So we'll interpret a negative supply to be a demand. And we can already see that in a case like this, assuming we've got a basic notion of balance globally, so that is to say, notice how there are 10 units of oversupply here, 4 units of oversupply here, 6 units of oversupply there. So my total oversupply is 20. And what's my total demand? Well, let's see. I've got 3 units of demand here, plus 5 units of demand there. That's 8. Plus 7 units of demand there, that's 15, plus 5 is 20. So the total supply and the total demand net out to 0. And you might notice that means it probably is feasible, I mean hopefully, to find some way of balancing all of the supply and all of the demand. In other words, finding a way for every vertex to end up with a net supply of 0. So an example would be, what if I send 10 units away from vertex D in this direction? Okay, in that case, vertex D has 0 left over. And now vertex I keep 5 units for vertex I and send 5 onward to vertex E. Okay, so now vertex E and vertex I both have 0. And so maybe we can see that if we find the right way of distributing the flow across the network by sending it between vertices, maybe we can find a way of setting the total supply at every vertex to 0, of completely equalizing supply and demand. And that is our ultimate goal. Now you might have noticed in the model I just worked out, we actually will have a problem because vertex A has a demand and there's nowhere that vertex A can get stuff from respecting edge directions besides vertex D. That's a sign that maybe the problem is a little bit more complicated than just, deciding to send 10 units up this way. So this supply imbalance, the fact that some nodes have supply and some nodes have demand, does sort of imply something that some statement we have to make about the global state of the network, which is that obviously if every node had a demand, had a non-zero demand, we'd be in trouble. There's no way of solving this. If no nodes have an oversupply, how am I going to equalize supply and demand? Now, similarly, although a little bit less severely, if we discover that no nodes have a demand at all, then I guess you could argue maybe every node has an oversupply, that's no big deal, because every node has enough. But I would argue that that's, for the sake of symmetry, that's also sort of a problem. So what we're going to do to begin with is assume that it's not a valid input unless the sum of all supply values across the entire network equals 0. It has to be exactly 0. So the total global supply has to equal the total global demand. There can be local imbalances, but across the entire network, there has to be an equilibrium, which means we can expect when we are done, if we're successful, that every single vertex ends up with a net oversupply of 0. That is a fundamental condition of this problem. Now, we'll see later that it's easy to generalize. It's actually very easy to generalize the problem to cases where there is allowed to be a global imbalance. For example, there could be more supply than there is demand. It's easy to generalize that, but it's much easier to generalize from the case where we assume the network is globally balanced than it is to generalize from the case where we are allowed to have an oversupply back to the case where it has to be globally balanced. So for now, for the rest of this sequence, we are going to assume as a fundamental condition of the problem that the input is not valid unless, when I add up the supply value of every single vertex in the graph, that I end up with 0 as the net supply. So the system is in global equilibrium, even if it's not in local equilibrium. And then finally, we're going to associate a shipping cost with each arc. As I mentioned earlier, the graph itself is only modeling the connection. We don't really know exactly why, for example, it costs 17 units to ship flow from D to I and only 7 to go from D to A. It could be that D and I are cities that are physically far apart, or they're separated by a body of water or something. We don't care. The graph is just providing us a way of modeling the bare minimum to solve the problem. So what we're going to do is attach to each arc this cost value. And the cost value represents how much does it cost to ship 1 unit of flow across this arc. So I mean, conceptually, if I were to send 10 units along this arc, it would cost 170. The costs have no inherent units, but I guess we could argue that it's $170 or something. I think I'm going to say that a couple of times inadvertently during this lecture. Okay, so now I have the complete specification of my input. And you might already realize we're going to have quite a hard time in this sequence of lectures talking about these problems, just because even to specify the input, I need so much information. So to summarize, I've got a set of vertices, a set of connections between vertices, the arcs of the graph. Each vertex has a supply value, where a negative supply is interpreted to mean demand, and each arc has a cost. Costs are allowed to be 0 or negative in certain situations, although that can affect whether the problem has a solution. For now, we're going to stick with costs that are strictly positive. And so the cost value of each arc describes the total cost of shipping 1 unit of flow across the arc. One note to make here is, unlike a lot of flow problems that you've probably seen in the past, there is no limit to how much flow I can send across an arc. So in other flow problems, like the ones you might have seen in CSC 226, you would have been told this arc has a maximum capacity of 10 units or something. That is not the case here. If I want to, I can send 10 million units of flow across this arc. I mean, it would cost, I don't know, $170 million. Hopefully I've got the budget for that. But there is no limit to how much flow I can send across an arc. Although you will probably realize that there is sort of an implicit limit implied by other parts of the problem, which is, we saw earlier that globally there is an oversupply of 20 in this graph. So it makes very little sense to ever be shipping any more than 20 units across a particular arc, because where would we be getting that flow from? But there is no inherent limitation imposed on any particular arc. No inherent upper bound or capacity on the arc. Okay, so when we have all of this information, we're now looking at an optimization problem. So our optimization problem is, I want to find some way to balance supply and demand. So I want to globally equalize supply and demand. But I also want to do so with minimum cost. So I know that there might be different ways that I could send flow between different vertices. I want to find the way that costs the least. So one example would be here, if I wanted to send 10 units from C up to I could send it this way, and it would cost $40, so 10 times 4. But I could also send it via H. I could send it up through H. And notice how if I go from C to I via H, it only costs 3 units to transport $3 to transport 1 unit of flow from C to I. If I were to transport my 10 units this way, that would only cost $30. And so we can see there might be multiple ways to balance my flows, and I want to choose the one with the minimum global cost. And that's what makes this a minimization problem. So here is an instance of a min-cost flow problem that we're going to come back to several times over the next few lectures. I have to sort of begin by wrangling notation a bit, or wrangling my presentation style to sort of account for all of the horrendous amount of information that I have to show. So the first thing is, there is no way of just representing everything we need on one copy of my graph. So starting now, I'm going to begin talking about these problems using this two-paned view. And this is one reason that the lecture took so long for me to prepare, is it wasn't just a question of what is the problem, it's also a question of, how do I explain this in a way that makes any amount of sense given the small rectangle I have to talk about stuff in this online setting. So what I'll do is, I'll put my initial input over here on the left, shaded in gray, supply and cost. This is the input graph. It is immutable. So you hand this to me at the beginning of the problem, and I never modify it. It's just here for information so that I have some context for things like how much does it cost to use a particular edge. As I work on solving these problems, my ultimate solution will take the form of an assignment of flow to edges. So for example, I might want to say, I want to send 3 units from E to D. And so we'll call this assignment of flow values to edges a flow. So a flow could be the amount that I send over a particular edge, or a flow could be a complete assignment of flow values to edges in the entire graph. I'll put that over on the right. We'll see by the end of part 2 of this sequence, we'll see that we actually end up incorporating a whole ton of other information into the right-hand side. So the right-hand side will be where I represent my working set of data, which will change over time as I converge on better and better solutions. We will eventually find a way of representing all of the mechanics of the simplex method in this right-hand pane using the graph with a graph theoretic interpretation. And so just the slides are now defining the thing I just said. Over on the right-hand pane, the labels on each edge are the amount of flow that I'm sending across that edge. So in other words, the total cost of what I'm sending from G to F will be, well, I'm sending 10 units of flow at a cost of $7 per unit. So I'm spending $70 to ship across the edge G to F. To ship from F to I, I'm sending 5 units of flow at $15 a piece, so I suppose that that's going to cost me $75. So that's the idea. I'm modeling over on the right the amount of flow, and over on the left, I'm modeling the cost of sending 1 unit of flow across the edge. If I therefore want to know how much the whole flow costs for the entire graph, I could just work that value out, the total cost for every edge, and just add all of those things together. And I think the slides are going to make me skip over something to show that. So here, yeah, the total cost of the flow I have here is $265. There's also these 2 points that we'll come back to a few times. There are 2 different constraints that we have to ensure get obeyed here. So one constraint is that the flow is balanced, and we're going to set this as our highest priority. So you saw the word feasible there. We'll get back to that in a minute. A flow is balanced if every vertex ends up in equilibrium, which means that basically when we account for all the flow coming in and all the flow leaving and whatever demand already existed, all of those net out to 0. The description given here is also valid, but I actually feel like just saying that they net out to 0 is a bit more intuitive. So to demonstrate that, we'll use vertex F for this. So vertex F had a total demand of 2. So it had -2 units of supply. But then I sent in 10 units from vertex G, which means now vertex F has 8 units extra. But then it sends 5 to vertex I, and it sends 3 to vertex E, and now you'll notice that that means it has 0 left over. So F is in perfect equilibrium. Similarly, G started out with 10 extra, but then I sent all of them away. So G is in perfect equilibrium. H started out with a demand of 6, but then it received 6 from I. So now H is in perfect equilibrium. I started out with an oversupply of 1, but then it sent out 6 units to H, which means I now has a deficit of 5, but then it receives 5 from F. And so it is also in perfect equilibrium. And if this holds for every single vertex of my graph, then we call the flow, the full assignment of flow values, then we call that balanced. And that is going to be our highest priority. We want to ensure at every step that our flow is balanced, even if maintaining balance requires us to do something that we're not allowed to do with edges, which brings me to my second definition, which is feasibility. A flow is said to be feasible if the amount of flow pushed across each edge respects the direction of that edge. This flow here is feasible. So if I ever attempt to push flow in the wrong direction across an arc, the full flow becomes infeasible. And there will be times when we choose to accept an infeasible flow for the moment so that I can ensure that the flow ends up balanced. It's more important to us to have balance than it is to have feasibility, at least in the early part. And the reason for that is because we have a mechanism in the simplex method. The word feasible is a loaded term. We know what that means. We have mechanisms in the simplex method to start from a situation that's infeasible in some way. So for example, primal infeasible, and arrive eventually at a feasible one. It turns out that arriving at a balanced one from an imbalanced one maybe is harder or doesn't fit as well into the framework of the simplex method. As a result, balance is more important than feasibility, at least early on. So if we were to ever send flow in the wrong direction along an arc, that would amount to basically having a negative flow value. If we have any negative flow values in our flow, then the flow is infeasible. You might observe that our definition for infeasibility in the traditional simplex method, or if we look at the linear algebraic representation, is indeed the same thing. If any of our variables have negative values, we consider the result to be infeasible. And that is one place, maybe the first place, where we might observe a couple of similarities between these flow numbers and stuff that we're familiar with from the simplex method. So this flow that we've already been looking at is both feasible and balanced, and its total cost is 265. It is a perfectly valid flow, although I will observe one interesting property of it, which is this thing. So this is not actually a cycle. If you stare at it, you might realize that you can't go all the way around in this cycle. But there is a certain amount of redundancy here. So I'm getting flow to B in two different ways. I'm getting it from E to B directly and from E to B sort of indirectly via these other three edges. It turns out what we'll see pretty quick, and I think in the second part of this sequence, is that this is actually unnecessary. There's some redundancy here that we don't need. And you might observe that if I can get flow from E to B in two different ways, I should just choose one of them. So for example, if I can go directly from E to B, that costs 8. If I go from E to B the long way, that costs 7. Which means I just shouldn't use, if I want to save money, I shouldn't use this at all. I should send all of my flow around the long way. And we'll notice that what this actually implies later is that in any flow that I care about that could be an optimal solution to this problem, I'm not going to see this type of construction. I'm going to have something that looks a lot more like a tree, that looks a lot more acyclic. But we'll get to that later. So a solution to this minimum cost network flow problem is a flow that is both feasible and balanced with the minimum total cost. So here's a different feasible and balanced flow. Notice how it does not have that funny cyclic sort of structure from before. It turns out the total cost here is 224, which of course makes it better, for minimization purposes, it makes it better than that example I had a minute ago. It turns out, I believe, this is actually one of the optimal solutions for this particular network, although how we figure that out, we're going to need some time to unpack. Okay, so the first question is, can we encode this? If you hand me this input graph, can we turn this into a linear program? The answer to that is emphatically yes. And in fact, if that's all we wanted to do, we could have talked about this in late May. Because turning this into a linear program is just a question of figuring out what your variables are and what your constraints are, something that we are very familiar with by now. The reason we left this topic until July is that after we do that, we're going to notice that the linear program looks so peculiar that it seems to justify us using a specialized form of the simplex method to solve it, as opposed to just throwing it at a typical off-the-shelf LP solver. Okay, so first off, what is our objective? I want to minimize the total cost across all arcs. Taking into account the flow that I'm pushing across each arc, I want to minimize the total cost. My input will comprise a directed graph, which gives me the structure of where the vertices are and how I'm allowed to move stuff between them. A function called supply, so if you hand me a vertex, I'll tell you the supply value for that vertex, keeping in mind that a negative supply value is meant to indicate demand. I'll also give you a function called cost, which if you hand me a particular edge, I'll tell you how much does it cost to ship 1 unit of flow across that edge. And then finally, this is just a notational thing. Here's a vertex V. In a directed graph, V might have several neighbors. So they're called X, Y, and Z. But V might also have several other neighbors over here. So A, B, and C. And these are both valid neighbors of V, but we do need to differentiate between them. So which neighbors can I access by starting at V and walking away? Which neighbors can I only access by starting there and walking towards V? Well, I'm going to define these to be the outbound neighbors of V. And I guess, these are going to be inbound. And so I'll use this function here, n of v, capital N of v, will be the set of outbound neighbors of the vertex v. I could define a second set for the inbound neighbors, but I like just working with the set of outbound neighbors. If I want to know what the inbound neighbors of v are, what I could do is look at all the other vertices and see which ones have v as one of their outbound neighbors. So I'm going to use this notation for that. It turns out, I think, this n of v never shows up again in this sequence, so we don't care too much, but there it is, just in case you were wondering. So my objective is to minimize the total cost across all arcs. Now the cost itself is fixed. I mean, it's a function, it's been provided as part of the input. So my optimization variables, I guess, will be how much flow am I sending across each arc. So what I'll do is I will define an optimization variable called XUV. for every arc. So every arc UV in E, which remember is an edge from U to V, for each one of those arcs, I will define an optimization variable to describe the amount of flow going from U to V. And maybe we realize that to respect the edge direction, I need this number to be non-negative. If it's negative, I'm sending flow in the wrong direction. But that sounds great, because we're used to enforcing that our optimization variables be non-negative. So what are my other constraints, besides that the flow has to be non-negative across each arc? Well, I also have to make sure that the global balance between supply and demand is maintained, which is to say, I need to make sure that when I take into account all the flow that leaves the vertex and all the flow that enters the vertex, what I'm left over with exactly matches the amount of supply that was originally there. And I think it might actually be more intuitive to rearrange this equation and write it like this. So if I take all the flow that's coming in and I subtract that from all the flow that's leaving, and then I subtract from that the total supply that was already at the vertex, I expect the global, the remainder to be 0 at every single vertex. So I need to enforce this constraint for every vertex in my graph. So I therefore am going to have, if I have a graph with m vertices, I'm going to have m constraints defined this way. Notice that this is an equality constraint. So what I'm doing is I'm enforcing this condition that the flow values that I come up with are in equilibrium for every vertex with the amount of supply at that vertex. So if a vertex has extra supply, all of that supply gets sent out somewhere else. So we can model this. Suppose a vertex has a supply of 7. If the vertex has a supply of 7, then I need to make sure that all 7 units of that supply get sent out to elsewhere in the network. In other words, I want the outgoing flow across all the different edges that are available to me from this vertex. I want the outgoing flow to equal 7. That's all I'm saying with this constraint. Similarly, if the vertex has a total supply of -5, so a deficit of 5 units, I want to make sure that 5 units are coming in from some other vertices. And of course, that this negative sign makes this -5. That's all I'm saying with these constraints. But notice that it's always an equality constraint. I need to make sure that the amount nets to exactly 0. There's this one weird thing that I'm going to insist on, and I'm always very suspicious of strange arbitrary steps like this. So I believe that this is the most intuitive way to write out this equality constraint, and it also looks sort of like the standard form that we're used to. I mean, it's not in standard form, but it does have all the variables on the left and a constant on the right. I think this is a nice way to write out this constraint. However, you can negate both sides of this. Because it's an equality, negating both sides changes nothing. If you negate both sides of this, you get this. And I hope you can agree these are identical. There is no semantic difference whatsoever between these two things. All I've done is negated both sides. Therefore, it is fair game for me to inexplicably decide that I like this version better. Now, to be clear, I actually don't like this version better. Negating the supply just seems unnecessary here. Hopefully you agree that this is exactly the same as this one. So for various reasons, I'm going to insist when we model this problem with an LP, we always use this formulation of the constraint. So we negate both sides and we put a negative sign on the right-hand side as a result. The reason I'm going to do that is later we're going to want to interpret the dual of these LPs. And for the sake of the dual variables making more intuitive sense, we want to get this negative sign out of there. So by negating both sides and putting a negative sign on the right-hand side of the constraint, what we end up with is, in the dual problem, we negate a coefficient in the objective function, which turns out to make very little difference to us. But it also means that this constraint system doesn't have as many negative signs in the wrong places, which makes it much easier to interpret the dual. So given that we've agreed that these are identical, and therefore I can choose either one of them, I am being upfront about the fact that I am insisting on this one, all else being equal, because it will make it easier for me to interpret the dual LP in the next lecture. All right, so we end up with this minimization problem. I want to minimize the total cost of the flow, which is equivalent to saying for every arc, multiply the cost of the arc by the flow across the arc and add everything together. I want to minimize that subject to the constraint that the flow is balanced at every vertex and that the flow is feasible, that I'm only sending flow in the forward direction along each edge. So here's our network from earlier. Let's take a look at the LP that we get for that. Well, there it is. And actually, I realized just before recording that I forgot to add the non-negativity constraint, but we're used to seeing that. So there's the LP. Now, I stare at this and I notice, sure, this is an LP. I could convert this to standard form. I mean, these equal signs have to be converted to make them into standard form. I could convert this to standard form and I could solve it with an off-the-shelf LP solver. That's it. And you know what? If this course were running out of time, I could just stop right there. We'd be done. On the other hand, I stare at this for a minute and I think, I've spent a lot of time in this course working on LP solvers. I've come to have a lot of respect for them. I've come to care a great deal for my LP solvers. They've really helped me out in my life. I want to look after them. And I'm worried that this might not really be a square meal for an LP solver. I don't think that it's very good nourishment, because usually the LPs that we solve are full of inequality constraints. They've got lots of nice coefficients in the constraint system. And this doesn't have any of that stuff. I'm worried that my LP solver isn't going to get a square meal out of this. Moreover, I'm a little bit worried that my LP solver might be overkill. So there are some reasons not only that an LP solver could actually have extra trouble with this LP, but also that a lot of the things that we're used to an LP solver, for example, with the Simplex method, a lot of the things we're used to it doing are completely unnecessary. So think about the fact that if you put this into dictionary form, it isn't so difficult because it's already got equalities everywhere. If you put this into dictionary form, you'll notice that there are no coefficients in the constraint system on any of the x variables besides -1, 0, and +1. And that means that when you go to compute your leaving variable, you do not need to do pretty much any of the complicated stuff that you would have had to do in an arbitrary LP. So the LP solver misses out on the joy of division to compute those ratios. It doesn't need to do that because the ratios are always going to be, well, the constant and then, over -1 or +1. And so our LP solver might be doing a lot of extra work, all these extra divisions to compute ratios that it doesn't need to do. Additionally, if we consider the way this constraint system looks, we might observe that if we contemplate it theoretically, our constraint system is defined based on edges. But each edge only participates in the constraint for 2 vertices because each edge only has 2 endpoints. So think about the edge from E to B. The edge from E to B, of course, will only participate in the constraint for vertex E, that would be this one, and vertex B, that would be this one. And so as a result, it'll turn out that every single column of my constraint matrix only has 2 non-zero entries. And that'll also imply that there are going to be a huge number of zeros in every row. Not necessarily, there could be more than 2 non-zero entries depending on the degree of the vertex. But the matrix, my constraint matrix, is going to end up being very sparse. One more thing that a typical LP solver isn't really optimized for. Now, there are linear algebraic solvers that can be optimized for this, but we might maybe conclude that there are a lot of reasons that this LP is unconventional, and because it's a very important application and we could generate graphs with thousands and thousands of vertices that would still produce an LP that looks like this, maybe it's worth considering whether we want to specialize our simplex method, both to avoid implementing extraneous features like all that division that we would be doing in a typical LP solver, maybe also to optimize some operations that this very equality-based constraint system could make difficult for a typical LP solver. And so I've just put this into linear algebraic form just to make it more obvious that this constraint matrix is very unusual looking. So before going into that, let me talk more about these equality constraints. I want to demonstrate why an LP that consists entirely of equality constraints can actually give quite a hard time to a dictionary-based simplex solver. And I'm going to do that with a smaller example. So this is a bit too clunky to work with, at least for the sake of illustrating stuff. So what about this LP here? And it's of the same form. It's maximization and not minimization, but that's not going to be a big deal for the time being. It's got 2 constraints, and they're both equality constraints, and a bunch of non-negativity constraints. Not much unlike the LP we saw for the minimum cost network flow problem. And normally we stare at an LP and we say, well, yeah, okay, there's 2 constraints, so I would expect my basis to have size 2. But maybe we recall that to convert this thing into standard form, we have to double up each equality constraint into a pair of inequalities because we know that our dictionary-based simplex method, as we know it at least, isn't really compatible with equality constraints. So first, we double up each constraint to be a pair of inequalities and then put those into standard form, and we end up with these pairs of inequality constraints. So now we went from an LP that has 2 constraints, where we normally would think, well, the basis should have size 2. We went to an LP, from an LP with 2 constraints to one that has 4 constraints. And now we're wondering, okay, is the basis supposed to have size 4? And maybe you've been thinking all semester, there is something a little bit odd about that, because we started with an LP with a specific number of constraints, and we ended up sort of exploding it outwards and introducing even more slack variables, to the extent we might be wondering, like, at what point do these extra variables actually get in the way of us understanding the structure of the underlying LP? If I convert this standard form LP to a dictionary, I get this, which is infeasible. And it shouldn't surprise us too much that it's infeasible, because if we look back at the thing we started with, we are saying that a linear combination of x variables has to equal something that isn't 0. So I suppose it's not surprising that we're not going to expect setting all the x's to 0 is going to make the result feasible. But one thing I would observe is, notice that because of those pairs of constraints that we constructed for the equalities, we now have pairs of related slack variables. In fact, it turns out that if we actually consider the relationship between W1 and W2, one of them is the negation of the other. W1 equals negative W2. We can reason quite a bit about this. So consider the case where W1 is basic. So certainly this is not feasible, because if W2 is negative 13, we've got an infeasible basis. But I want to talk about W1 and W2 in general. Notice that if both W1 and W2 are non-zero, because one has to be the negation of the other, if both W1 and W2 are in the basis, I can expect the basis is going to be infeasible, unless they're both zero, unless they're both degenerate basic variables. If one of them is non-zero, the other one's going to be its negation, and that means that at least one of them will be negative, which means that the basis will not be feasible. Were I to take this initial dictionary and then find a feasible dictionary, I end up with this. And if I stare at this for a minute, I notice something quite unusual, which is that I remember those pairs. We had the pair W1, W2. There's my old W problem coming back. W3, W4. Notice that in this dictionary, this feasible dictionary, exactly one of each pair is in the basis, and the other one is not. But despite one of each pair being in the basis, both of those cases are degenerate, which makes sense, because since I said a minute ago that W1 equals the negation of W2, if W2 is non-basic, then it has to equal 0, which means W1 has to also equal 0. So it shouldn't surprise us that if one of the pair is non-basic, the other one has to be basic and degenerate, or I guess it has to be non-basic. So because each of these pairs are the negations of each other, either both will be basic or both will equal 0, because if one is non-basic, the other one has to equal 0 as well. And if it were the case that both were basic and non-zero, then one of them has to be negative, which makes the dictionary automatically infeasible, which means in any feasible dictionary, both of the pair have to be 0, whether they're basic or not. But we can go further, and we can observe that, okay, so in this case, one of the pair W1, W2, in this case it's W2, is non-basic. The question is, okay, given that W1 and W3 are going to be 0 anyway, is there a way I can get them out of the basis? And the answer is no. Think about it. How would I get W1 out of the basis? Well, it would be the leaving variable. Okay, so what's the entering variable? Well, it's sure not x2, and it's sure not W4. The only variable that would be a valid entering variable to pivot out W1 is W2. But that'll defeat the purpose. If I pivot with W1, W2, then one of this pair is still going to be in the basis. And maybe you'll realize what this means is that under all circumstances, it is impossible to get both of the pair out of the basis. One of them always has to be basic, because there simply is no pivot that would get us both of them out of the basis. And the same is also true in a linear algebraic solution, so it's not just the dictionary thing. In the linear algebraic simplex method, the same thing happens. You justify it more in terms of the linear independence of constraints. And what this brings us to is, if one of the pair always has to be basic, and that in any feasible basis, these slack variables always have to equal 0, what we've ended up with is observing that these slack variables are completely useless. They have no meaning whatsoever. They're sort of ballast, because they're always going to equal 0, and one of them always has to be in the basis. Which means, even though my basis apparently has 4 slots, 2 of them are always going to be taken up by these meaningless placeholder slack variables that are always going to equal 0. And if we scroll all the way back, and we consider my original LP, which had 2 constraints, where I said, hey, an LP with 2 constraints, it sounds like the basis is going to have size 2. Well, once I'm done all this manipulation, it turns out that it does. because the basis is expanded to have size 4 by doubling up my constraints. But then, due to the weird behavior of the slack variables, 2 of my basis slots are completely off limits, which means my real basis still ends up actually having size 2. And that's just the result of doubling up the constraints. In a sense, having these 2 basis slots get locked down like this sort of cancels out the effect of doubling those constraints. It brings the resulting dictionary back into line with what we would expect for the original LP. And so we can definitely solve these LPs. I mean, we know already we can convert any LP to standard form and we can solve it. And if it has a feasible solution, we'll find it. And if it has a feasible solution and it's bounded, we'll find the optimal solution with the simplex method. We can do that. But notice that if my LP is full of tons and tons and tons of equality constraints, I am going to have tons of these meaningless ballast rows in my basis, which in and of itself isn't really a problem if they're just there to take up space, if they're just dead weight. But notice that although this basis row will always be 0, one of W1 or W2 will always be in the basis and it'll always equal 0. Although that's the case, it is true that it's not quite dead weight because W2 has a positive objective coefficient, which means I might make the mistake of pivoting with W2 and then pivoting W2 and W1 and wasting time, doing a degenerate pivot. And if I have a ton of equality constraints, it is quite reasonable that I might expect my simplex solver to waste a lot of time treading water, hopefully not cycling, but certainly waste a lot of time treading water with a bunch of meaningless degenerate pivots. That's one reason why if I have a ton of equality constraints, it might be nice to optimize my solver a bit to handle that. Now, to be clear, there are lots of ways of optimizing solvers for equality constraints that don't involve the network simplex method. But this is one more point in favor of maybe developing a specialization of my algorithm for the network case. So the main observation out of all this stuff was if I have an LP that consists of tons of equality constraints, I can add slack variables, which does help me with a couple of things. It allows me to use my dictionary-based method, but they're always going to equal 0. And they have no meaning because if they're always going to equal 0, I have no way of interpreting them. They're just a bunch of variables taking up space. They're just placeholders, essentially to wall off a certain number of slots in my basis. Now, we have a couple of ways around this. So one real observation to take out of this is that in the case where my LP is just equality constraints, the slack variables are meaningless. So why have them at all? Well, we could argue if you hand me an LP that already looks like this, so it already has an equal sign and no inequalities, then maybe I should just use that directly as my equational form. So we saw last week that if you give me an arbitrary LP, I can always build an equational form by grafting on this identity matrix over here, which represents every slack variable. And if I do that, I mean, that's how I introduce slack variables to handle inequalities. What I'm claiming here is that because the point of developing equational form is to put an LP into this form here where it's an equal sign and not a less than or equal to sign, what I'm arguing is if you hand me an LP, slack variables or not, if you hand me an LP that already looks like this, I could just use this as the equational form directly. So I wouldn't need to use slack variables or create extra slack variables at all. If I do this, I should expect if A has m rows, then I should expect that my basis will just have size m. And furthermore, that every single basic variable at any point will be an x. It'll be an optimization variable for the simple reason that I did not add any slack variables. And that works. I am allowed to do that. There is one caveat we have to consider, something that we've been ignoring all semester, which is that last week we spent all this time talking about this basis matrix AB. And I think I'm going to make up a new slide here. Okay, so here's our big equational form matrix A. And we choose some basis. So we decide that x2, x3, x4, and x7 are the basic variables. And that implies, of course, that A has 4 rows. Okay, so we choose these. And we saw last week that, of course, for this to be a valid basis, we need this basis matrix that we construct called AB. We need this to be invertible. So that's a precondition of something even being a basis. Feasible or not, the matrix has to be invertible or we don't have a basis. The issue here is that if you hand me an arbitrary matrix A, so if you give me an LP that is already in this form with some matrix A, I need to make sure that A has full rank. So that the rank, so in this case, if A has, I guess A has 4 rows, I want the rank of A to equal M, which in this case equals 4. I need that because if the rank of A doesn't equal 4, then any collection of columns that I take and put into AB is also not going to have rank 4. And if AB, which is going to be, so AB is 4 by 4. If AB is a 4 by 4 matrix and it does not have rank 4, then it is not going to be invertible. So if the big matrix A does not have full rank, then there's no way that the matrix AB will ever, for any choice of basis, have full rank, which means it'll never be invertible. Now, the reason why this could happen, the only reason why I would expect that my matrix A would not have full rank, is if some of its rows are linearly dependent on others. What that really means is that some of my constraints are redundant. Some of my constraints are just linear combinations of my other constraints. And those are completely redundant. I can ignore them. And so it turns out I have a remedy in this case. In the event where A does not have full rank, what I can do is just delete those redundant constraints. So I end up with a smaller matrix, a matrix with fewer rows. I keep deleting linearly dependent rows of A until the rank of the resulting matrix is full, and then I have a matrix that I can work with. And that'll give us a matrix with full rank. Now, I guess it's worth, I guess I already said that here. It's worth considering, why did we get to ignore this until now? If redundant constraints can create such a problem with invertibility, why are we allowed to ignore it up until early July in a linear programming course? And the reason is, with the constructions that we've been using, where we create extra slack variables, or in the linear algebraic version where I graphed on this identity matrix, maybe you'll notice that if I stick an identity matrix on here, I'm guaranteed to have linearly independent rows when I'm done, for the simple reason that each row has this 1 in it in its own special column. So there's no way that any collection of rows from this augmented matrix can be linearly dependent on each other, because no two rows have a 1 in the same column over here. As a result, if I use the construction where I add slack variables, I'm sort of padding out the matrix to always have full rank. So there's no way I'm going to run into that problem of having redundant constraints if I always use slack variables, because I have a separate slack variable for each constraint. That's why it wasn't a problem until now. That's also why it wasn't a problem in the dictionary-based method where I always add slack variables. And you might be asking, okay, so wait a minute, there's two sides to this coin. If I add slack variables, the rank is always full, so it's no big deal. If I don't add slack variables, I might have a problem with rank. So in that case, let's just add the slack variables. Well, that's a good point. The reason I want to avoid adding them is there's an interpretation we're going to use of the network simplex method where not having any primal slack variables really makes our life easier. And that's why I want to broach this sort of odd aside now, so late in the course. The other thing I want to talk about is, when I have an LP of this unique form with equality constraints only, what does the dual look like? So we know, hopefully, that we can easily derive a dual for this LP. We first convert it to standard form, which is to say we double up each constraint. We then take the dual of that, and we stare at it a while and see if we can simplify it a bit. So if we convert this to standard form and take the dual, the standard form version of this LP here is going to have 4 inequality constraints, which means its dual is going to have 4 dual optimization variables, 4 y variables. However, it turns out that there's an observation that we can make about those y variables that allows us to condense them back down. And I'll talk about this, I think, in a live session. I don't think it makes much sense to make this lecture any longer by going through the full derivation. The book talks about it too. It's not as much of a network thing as it is just sort of an implication of duality. You may recall that if we ever have a variable, let's call it w, if I have a variable in my LP that is unconstrained, so if I were to have a variable with that can be positive or negative in an LP and I want to convert it to standard form, what we do is we double up the variable to create two different sort of the negative and positive parts of W. We convert the unconstrained variable W to this difference W plus minus W minus. So we just double up on variables. And then we can constrain both W plus and W minus to be non-negative. It turns out that if you compute the dual, if you put this into standard form and you compute the dual, you end up with an LP that has 4 optimization variables. But if you stare at them carefully, you realize that if you pair up the optimization variables, in other words, if you pair them up the same way the constraints resulted in pairs of inequalities, you actually can do that same transformation, the W plus minus W minus thing, in reverse. And so when all is said and done, when the dust settles, the dual of this LP is actually this thing. And notice this unique characteristic where it's got unconstrained dual optimization variables. That means any solution that satisfies these three constraints is feasible, even if the y's are negative. So the key thing there is, because I had only equality constraints in my primal, my dual optimization variables end up being unconstrained. Now, there is something about this. I mean, hopefully you can take my word for it. The book does go over this derivation. I'll talk about it a bit as well in the live session. There's something about this that is a bit asymmetric. We're used to the dual and the primal sort of looking like mirror images of each other, or mirror images but like diagonally transposed or something. And yet over here we have an equal sign, and over here we have a greater than or equal sign, which just doesn't feel right. We found some way of reducing it so it only has two optimization variables. That's certainly reassuring. Wouldn't it be nice if we could find some way of incorporating equal signs as opposed to greater than or equal to signs? And recall that when we've eliminated greater than or equal to signs or less than or equal to signs in the past, the way that we've done it is with a slack variable. So if I have this constraint y1 plus 2y2 is greater than or equal to 1, well, what I mean is that this sum here there'll be some distance between this sum and the number 1. So what I could do is I could say, well, what we'll do in a dictionary, for example, is fold in some slack variable. So I'll, minus z equals 1. So y1 plus 2y2 minus some positive number will always equal 1, where this could also be 0, I guess. So that's how we resolve that problem in dictionary form. But what's stopping us from just folding slack variables directly into my LP? Well, nothing. I could do this. I could convert any LP to a strictly equality-based form by just introducing slack variables directly into the statement of the LP, and that's what I'm doing here. So I have the dual of this primal problem with only equality constraints, and that dual, once I fold in, notice how there is a separate slack variable for each line. They're all lined up in a column, but they are three separate variables. When I fold that in, I have a dual with these weird unconstrained dual variables and extra slack variables that I've added, but it does have equality constraints everywhere. And the idea behind this is, if I'm going to begin talking about a specialization of the simplex method for these LPs that only have equality constraints, I think it's to my benefit to try and make sure I only have equality constraints everywhere, that I don't have to worry about any other kinds of constraints besides the usual non-negativity things and these linear combination equality constraints. Now, what we'll discover later with the specific case of the dual of these network flow problems is that there is actually a meaningful interpretation of these y values. So for our minimum cost network flow problem, in the primal LP, there is one optimization variable for each arc, and there is one constraint for each vertex. And it turns out that there ends up being one dual optimization variable for each vertex and one dual slack variable for each arc. And they both have an interesting and intuitive semantic meaning. On the other hand, the primal slack variables, which don't even exist at this point, are useless. So that we're not even going to worry about the W variables in the primal problem. We don't need them. I actually already answered this question about 3 slides ago, so I'm going to ignore that. One final note. So you may know, I guess from assignment 3, that computing the dual of a minimization problem requires a tiny bit of a different derivation because you have to do a couple of sign flips. And if we compute the dual of a minimization problem in this form, which is what we want to do because our primal problem is the minimum cost flow problem, if we compute a dual of a problem in this form, we end up with this. So the key difference, because of those sign flips, is that our slack variables are added, not subtracted. So it's plus Z1 as opposed to minus Z1. Strangely, the sign flips don't really affect the Y values. And the reason is because since the Y values are unconstrained, they could have been positive or negative to begin with. So by doing sort of a substitution where we just assume that, Y, like we just take the negation that we got and just call that Y, we're able to avoid, having to change anything in either of these two columns. The sign flip does still affect something, but it's something that we can filter out before we get to our final expression of the dual. If our goal had just been to find a way of solving our minimum cost network flow problem using linear programming, we could stop, well, not here, we could have stopped like 20 slides ago. And there are lots of other variations that we can also convert directly into regular old-fashioned looking linear programs. And we'll see those, I don't know about shortly, we'll see those eventually. The issue here is that we've seen a lot of reasons why the LPs produced for these network flow problems are sort of unique. They're interesting. And a lot of the other variants of network flow problems produce similarly interesting LPs with equality constraints only and with these coefficient matrices that only have ones and negative ones and zeros in them. And there's also, we've noted that there are lots of reasons why a typical LP solver might get into trouble solving some of these LPs. It still might be able to do it, but it would be frustrating because some of the features that we build into LP solvers, like all the divisions that we do to compute the ratios, we wouldn't need. And also, because of those equality constraints, there could be tons and tons of degenerate pivots, which could waste lots of time. And because the coefficient matrix is relatively sparse, we would want an implementation at least that's optimized for sparse matrices, something that we haven't actually seen directly, although I alluded last week to the idea that you can implement the revised simplex method in a way that is optimized for sparse matrices. So there are lots of reasons why maybe we should try and find a way to implement a specialized solver just for these network flow problems. And we can go further from there. We can think, well, if we're going to do that, let's see if we can find a way of solving the network flow problem using the graph. Let's not even worry about a dictionary. Let's not even worry about the linear algebraic simplex method. Let's see if we can use, not only apply the simplex method to the graph, but make the simplex method part of the graph. Find a graph theoretic interpretation of our simplex method. What we'll see, for example, is that we will discover quite quickly that our basis, which is actually going to be a collection of edges of our graph, forms a spanning tree. And that choosing pivots involves talking about things like connected components and cycles in the graph. So deriving a graph theoretic interpretation of our simplex method not only will allow us to solve this problem more efficiently, it'll also allow us to drag in a bunch of interesting stuff from the area of graph algorithms, stuff like how do I find a cycle, how do I compute the components of a graph. And just like how last week, computing a linear algebraic version of the simplex method allowed us to bring in stuff from numerical linear algebra. Finding a graph theoretic interpretation of the simplex method, which we are going to call the network simplex method, will allow us to bring in graph algorithms, which are more efficient at being able to identify these graph theoretic structures like paths and cycles and things than might be possible with the linear algebraic interpretation available to a typical simplex solver. So in the next lecture, we're going to talk about deriving that graph theoretic interpretation of each aspect. We already have a head start. We know that the primal optimization variables, x, u, v, each of those represents the flow across a particular arc. Our goal is going to be to find a quick way of computing balanced flows given a basis, and then to find some interpretation of the y and z variables, the dual optimization variables, one per vertex, and the dual slack variable z, one per arc. And then once we have a graph theoretic interpretation of those, find some way of deriving the pivoting procedure that will produce our network simplex method.